Good morning. As Marco said, my name is Nick Martin, and I'm a content engineer here at Markforged. And we're going to be talking about 3D printed composites and what advantages they can bring to your production cycle. All right, so by the end of this webinar, you're going to understand the difference between 3D printed composites and thermoplastics, and you'll understand the basic components of a composite. And you'll also be able to describe how composites are 3D printed and be able to name some of the properties and applications of different 3D printable composite materials. So a lot of you have probably heard of 3D printed thermoplastics. Most materials that are 3D printed fall under this category, and none of them have really proven strong or durable enough for industrial applications, which is why we started 3D printing composites, which outperform thermoplastics in every material property category that you can think of. For example, Markforged's 3D printed carbon fiber reinforcement is more than 8 times stronger than ABS, which is a popular 3D printed thermoplastic. So also included on this graph are nylon and PLA, which are other common 3D printed thermoplastics as well. When it comes to stiffness, no thermoplastic comes close to matching up with carbon fiber. Carbon fiber is about 24 times more rigid than ABS and around 60 times more rigid than nylon. Here is so high strength, high temperature fiberglass, another reinforcement fiber from Markforged, exhibits excellent impact resistance, about 30 times more than ABS. We're going to get more into specific properties of each of these reinforcement fibers later in the webinar. But first, I want to cover what I'm talking about when I say composites and thermoplastics and how your understanding that you have already may fit in with the kind of 3D printing that Markforged does. So thermoplastics are plastics that melt when heated and harden when cooled without a change in their chemical properties. They're popular 3D printing materials because they can be easily melted, extruded layer by layer, and then immediately cooled into any desired shape that you want. Most thermoplastics have a relatively low melting point, which makes them easier to print, and are typically very flexible. This picture shows a thermoplastic bending at a 90-degree angle when there's a load applied to the end of it. That really shows that flexibility of thermoplastics. Composites, on the other hand, are made up of more than one material that, when combined, have properties that are different from each of those individual materials. So there's 2 main components of composite parts, a matrix and a reinforcement. So for typical fiber composites, the reinforcement, like carbon fiber or fiberglass, for example, is formed into your desired shape and then covered with the matrix, which could be an epoxy or a thermoset plastic. And that helps it retain its shape. So you can see in the picture to the right, the black woven material is carbon fiber, and that brush is applying the matrix to it to make it a composite part. And these methods yield really strong, stiff, and lightweight parts. So just like any other composite parts, Markforged 3D printed composites are made up of 2 components, a matrix and a reinforcement. Our matrix is called onyx. It's a nylon-based thermoplastic mixed with chopped carbon fiber, and the reinforcement is any one of our fibers. This picture, it is Kevlar. So composite parts are printed layer by layer using a process that we call continuous filament fabrication, or CFF for short. This 3D printing method involves 2 extrusion nozzles. So one of them is dedicated to printing onyx, which is that matrix material, and the other is printing the reinforcement. This picture is a photo taken from above of a print paused halfway to show that fiber routing along the edge. The black is the matrix, which is onyx, and then the yellow is that Kevlar reinforcement. So here's a view from above of one of our desktop printers. And right there highlighted in yellow is the print head. And so on the bottom of that print head is where the two nozzles are located. The one that's dedicated to thermoplastic and the other one to continuous fibers. And the two tubes that you see on the top of that head highlighted in yellow are the feed tubes for the material into the print head. So one tube is for the tube in the front is for continuous fibers, and the one in the back is for thermoplastic. So this method, CFF, is really what gives Markforged the parts the incredible strength. So when loaded, that reinforcement fiber distributes the load along the length of the fibers, while the matrix hold those fibers in place, which allows you to have parts that are actually more rigid than the thermoplastic or fiber alone. Here's a video of that strength in action. On the left of the video is a fiberglass reinforced onyx beam, and that's printed on a Markforged printer. Second from the left is onyx, so just the thermoplastic without any reinforcement. And the other two are typical 3D printing thermoplastics, ABS and PLA. 7.5 pounds was hung from each of the beams. And while both the ABS and PLA beams snap into, the composite beam deflects a little bit and then goes back to its original shape after the weight is removed. The difference between composites and stronger thermoplastics is really well illustrated by looking at that unreinforced onyx beam. So although onyx is stronger than most other thermoplastics, when reinforced with continuous fiber, it becomes a lot stiffer and less ductile. So as we've seen, continuous fibers allow for 3D printed parts strong enough for industrial applications, unlike just thermoplastics. And just as with all other engineering materials, it's important to understand the properties of each of these reinforcements in order to know how to leverage their advantages. So now we're going to explore each of Markforged reinforcement fibers to learn where they can fit into your production cycle. The first up is fiberglass. Fiberglass is what we call our entry-level reinforcement fiber. It's our least expensive fiber. And it's already 3 times stronger than ABS and is 11 times more rigid than ABS. And so this is a really good starting point for people to who are looking to start printing engineering grade parts. Fiberglass is our most cost-effective one. Here's the video again that was showcasing fiberglass's strength and stiffness. And then, so fiberglass, because of its really good strength and stiffness, it's a great go-to general use fiber. So when you need more strength than thermoplastics, but not quite the robustness of metal, you can use fiberglass. So example applications that our customers use are functional prototypes, brackets, drill jigs, and soft jaws. So here's an example of a fiberglass reinforced soft jaw in action. So custom soft jaws are a really good way to precisely hold irregularly shaped parts when you want to machine them. So when onyx is reinforced with fiberglass, the 3D printed jaws are stiff enough to keep the part from moving around when you're machining it, but soft enough to have a non-marring surface so you don't mess up the part from the clamping force. In this particular case, the jaws are holding a needle bearing housing, which is undergoing a facing operation on the mill. The next material we're going to look at is carbon fiber. It has the best strength to weight ratio out of any of our fibers, with a strength to weight 50% higher than that of 6061 aluminum. In fact, the strength of carbon fiber is so high that when we print it, its strength is equal to the yield strength of 6061 aluminum. So what that means is it fails at the same stress that aluminum starts to plastically deform. It's also our stiffest fiber. It's 24 times more rigid than ABS and 60 times more rigid than nylon. So in this video, 27.5 pounds of weight is hung from a 7-gram carbon fiber beam. And then the same weight is hung from a 12-gram 6061 beam. And so you can see that the composite part deflects very minimally and then returns back to its original shape when that weight is removed. And that aluminum beam begins to yield as that weight is placed on it. And when the weight is removed, it doesn't return back to its original shape because it has started to plastically deform. So because of these really amazing properties, carbon fiber is ideal for situations when you want the absolute highest stiffness and lowest deflection. It's strong enough to replace aluminum at nearly half the weight. So our customers typically use it for tooling, fixtures, and end-use parts that would otherwise be machined out of metal. So this is one of our customer examples. It's a company called Haddington Dynamics, and they developed Dexter, which is a 3D printed robotic arm, and it's almost completely made out of 3D printed Markforged parts. And they use carbon fiber reinforcement for the arm because it's the only material that's stiff and lightweight enough to keep the precision that they want on this robotic arm, which is 50 microns, just about 0.02 of an inch is the precision of this arm in 3D space. Our next fiber is Kevlar. Kevlar is extremely durable, which means parts reinforced with it can really take a beating without failing. It's also 15 to 20% lighter than the rest of our fibers, depending on what fiber you're comparing it to, making it the least dense out of all of our reinforcement fibers. Kevlar also has the ability to plastically deform without losing strength. So this means a couple things. First, it retains a really high strength while allowing some give in the contact loaded surface. And secondly, it has the least catastrophic failure mode compared to the rest of the fibers. So for example, carbon fiber, as we talked about, deflects very minimally. But what that means is that it's brittle. So when carbon fiber is loaded to its maximum, it fails completely and basically with no warning. Kevlar, on the other hand, it deforms until fibers begin to fail one at a time until it eventually fails. So this provides a lot more predictable and forgivable failure mode. Here's a video of me literally beating Kevlar with a hammer. The blue part is ABS and the red one is PLA. And the black is Kevlar reinforced onyx. So this really showcases that amazing impact resistance that onyx has and that durability. It's just completely above and beyond typical thermoplastics. So because of this really low density and high durability, Kevlar is great for applications involving a lot of motion and interfacing with production parts. So our customers use it a lot of the time for end effectors. One of our customers actually 3D prints the entirety of their crash test dummy skeletons with Kevlar reinforced parts. One specific customer example is Dixon Valve. They print Kevlar reinforced grippers as end of arm tooling for one of their robotic arms. And this robot, it transfers fittings between machining centers. And so Kevlar's toughness combined with its low density make for really lightweight jaws that can withstand repeated clampings. So the last material we're going to talk about today is one that's pretty unique to Markforged, and that's high strength, high temperature fiberglass, or we call it HSHT for short. So HSHT has superior heat resistance. It retains its strength at temperatures above 300 degrees Fahrenheit, around 150 degrees Celsius. That's well past most thermoplastics glass transition temperature and about 80 degrees Fahrenheit higher than any of our other fibers. HSHT also has incredible impact resistance, 30 times that of ABS, as I mentioned earlier. Additionally, HSHT can elastically deform more than any other fiber. So this is special because as HSHT is loaded towards its maximum, it deflects. And then if you unload it, it will still return back to its original shape, which is what I mean when I say elastically deform. And so this is really helpful for parts that need that high elasticity, or parts that will be repeatedly deflected and need to go back to the original dimensions. So before this video was shot, each of these beams was heated in an oven at 140 degrees Celsius, which is about 285 Fahrenheit. The HSHT reinforced beam retained its strength and stiffness, as you can see, and it was able to support 5 pounds hung from the end while deflecting a little bit, whereas PLA and ABS actually started to deflect under their own weight before the weight was even hung from the end. And then you can see they basically were pretty limp as we put the weight on. And so the thermal properties of HSHT in a 3D printed part really unlocks a lot of new applications for 3D printing. Here's some examples of what our customers are doing with it. Welding fixtures are really popular. Thermoforms, thermoset molds, injection mold inserts, and blow molds. And so all of these applications are either high temperature or high impact or a combination of the two. And the reason we can do this with HSHT is really because of that high strength and that high heat deflection temperature. So here's a customer example. Humanetics is the leading manufacturer of crash test dummies, and they use our printers to fabricate actually a lot of things in their production cycle. But one thing they do is thermoset molds for a protective neck ring that goes on their adult dummies. And this neck ring is a pretty complex shape, and they used to make silicone molds for it, but those were not durable enough. And so HSHT's ability to really retain that strength and rigidity at high temperatures made it a really good reinforcement fiber for this application. All right, so that does it for our webinar on composites today. Whether it's the low density and that high durability of Kevlar or that excellent rigidity that carbon fiber has, 3D printed reinforcements give you really a diverse set of properties that can be leveraged to your needs depending on what fiber you choose. And so now I think we're going to take some time to answer questions from you all.
Yep. So just before we do that, we did have a few questions about being able to watch the webinar afterwards. We have been recording today's webinar, and we will be distributing a link to the recording within about a day. So expect a link to arrive via email for you sometime tomorrow. So we've been getting some pretty great questions. If you have questions, there is a Q&A button in your interface. Just click that, and it'll open a window where you can ask your questions. And I think with that, I think we're going to go to Q&A.
Great. So one of the first questions we got is how the direction of the printing affects the strength of a part. And that's a really good question. So this is true generally for all 3D printed parts, is in the Z direction along the axis of the layer lines, parts typically have less strength than in the XY direction. And because of this, when you're 3D printing parts, it's good to plan the orientation of which you'll print it to really get that maximum strength. Let's see. Okay, this is another really good question. What is the role of the chopped carbon fiber in the onyx? So what chopped carbon fiber does is it gives, so onyx is nylon based, as I said, and when you add chopped carbon fiber, it gives it just a little bit more stiffness and strength, not quite as much as the continuous fibers do, but enough to put it above other thermoplastics from the get-go. Oh, great question. Are there any health concerns when printing or special requirements to the room where you print with carbon or Kevlar? No, there are not. So I actually sit next to 5 3D printers in the office that I print on all day. These are completely safe to print in an office environment. And we've designed our methods to be safe and handleable with your bare hands to be as usable as possible. Another question is, can you fill with metal fibers? No, all of our fibers are the ones that I went over today. But if you're interested in metal 3D printing, we do have a full metal system called what's based on our printer, the Metal X. And so you can check out our website to learn more about our metal printing if you're interested in that. Let's see. Oh, okay. So a couple questions on HSHT, if it deforms at 350 Fahrenheit. So with thermal properties, it's pretty interesting. The heat deflection temperature is a common property that's discussed. And that's kind of an arbitrary measure, but with HSHT particularly, once it gets over 300 degrees, between about 300 and 350 Fahrenheit, it decreases its stiffness and strength to a little over 50%. So it still has most of its strength over 300 degrees Fahrenheit, whereas materials like PLA or ABS lose more than 95% of their stiffness at temperatures that are much lower. Let's see. Another question on combining fibers in the same part. No, you cannot combine fibers in the same part. You load them individually depending on the part, which typically works out for your application.
Give us, if we pause a little between questions, we have a lot of them coming in and the windows jumping around.
A couple of questions on filament costs. Those are all included online, and you can check those out on our website if you would like. This is a good question. What products run on which machines? I'm assuming that's asking which fibers can be printed on which machines. So our Onyx 1 and X3, which is the industrial series, print just Onyx, whereas the Onyx Pro and the X5 print Onyx plus fiberglass, and then the X7 and Mark II print our entire suite of fibers. And those printers are upgradable. So if you start off with one of the less expensive ones and decide you want to print in more fibers, you can always upgrade as well. Oh, a good question on what control do I have over the placement of my continuous fibers within my prints. So our 3D printing software, Eiger, aids you in this. And Eiger's, you can actually check it out on our website, but Eiger basically allows you to choose how you want the fiber to route based on how your part is loaded. For example, if your part will be loaded in bending, you would choose concentric fill, and it automatically lays the rings of fiber around your part, kind of like how you may have seen on that end effector. Or if you want it to have an isotropic strength, then you can choose that sort of fill, and it will automatically route how the fibers will be to give it that isotropic strength. So it really, our software really aids you in how you want to lay those.
This is actually a great point for everyone listening today. If you'd like to see how your parts would look with fiber reinforcement, you can actually visit us at markforged.com, and you can actually sign up for a trial of our Eiger software. It's an unlimited trial. You can use it as much as you want. It's totally free as well. And you can log in and you can upload your own parts, and then you can actually have the software slice them and choose the fiber reinforcement and actually play around with where in the part you would like your fiber reinforcement to go. And that's a great way to both learn about how our fiber configuration system works, as well as see your part print times and part cost with different fibers in them. Because I actually see there's another question about how long it takes to print with various fibers. You can actually upload your own parts because, of course, this will depend on the part geometry. But you can visit us at markforged.com. You can log into the software. You can upload your part, and you can actually get an estimate of how long it'll take to print with various fibers.
Yep. Thank you, Marco. And so moving on, another question about chemical properties. Each of these fibers do have different properties in terms of chemical resistivity. But keep in mind that the matrix, which is Onyx, is the part that will be coming in contact with any chemicals, and Onyx is extremely chemically resistant. You can check out our data sheet to find out more, but it's used, a lot of our customers use it in their machine shops So you can check out more info on that on the website if you would like. Let's see. Another question on how you design parts in CAD to account for the fiber. As we mentioned, you don't have to account for it in CAD. That's all taken care of in our software. One question, what temperature can the carbon fiber printing go to? I'm assuming that means what are the max temperatures the carbon fiber can withstand? The heat deflection temperature of our carbon fiber is over 100 degrees Celsius, so it's around 220 Fahrenheit. Anything higher than that temperature, you would probably want to use HSHT instead.
See, there's a question here about contact information for our application engineers. If you are interested in discussing your particular applications for this process, you can again visit us at markforged.com and you can fill out a form to get in touch or request a consultation. And this will connect you with one of our specialists who can actually learn more about what you're trying to do, and if there's a good opportunity for us to be able to help you out with what you're trying to get done, we can actually connect you with one of our application engineers who can take a look at what you're trying to build and discuss your part with you. So I see actually a few more questions about the software. You actually, there's a question about, does the software manage the strategy for the fiber laydown, or does the user have to define? You can actually fully configure. There's a few defaults that come into play when you upload a part, but you actually have a lot of control over the configuration of fiber within your part.
One good question on, can you integrate steel pieces for reinforcement in 3D printed parts? And this brings up a really good point. So when you 3D print on our printers, you can actually integrate a pause into the print at any layer that you want. And some of our customers, what they do is if they want to put steel or some sort of hardware inside of their print, they design for it in CAD to have a cavity. They pause the print, and then you can actually take the bed off, put those steel or hardware pieces into the print, and then it will print around it. And so this is really good if you want to integrate other hardware into your printed pieces, just like you would in any other assembly that you'd make. A couple more questions about fiber and how it's laid and minimum radii that it can print in. We actually have a fiber design guide, a composites design guide on the website that you can check out, and that's got a wealth of information on how you can best design with these fibers.
And in fact, I think that's a good thing for me to include in the email. So everyone here who's registered for today's webinar is going to get an email with a link to the recording of today's webinar. Expect that. It takes about 24 hours to process that and send it out. So expect that sometime tomorrow. But I'll make sure to include a link to the Composites design guide in there as well.
One question, can legacy printers be retrofitted for composite feed heads? So as I mentioned, if you buy one of our printers that does not print our full suite of fibers and you decide later that you do want to print in carbon fiber, for example, our printers are all upgradable. Another question on corrosion resistance. If we have customers with corrosion applications for the 3D printed parts, yes, we do, both on the metal and the composite side. And we've had good results. Like I've said, a lot of our parts are used as tooling and fixturing. So whether it's as a welding fixture or in the machine shop and it has to withstand, a lot of lubrication fluids, a lot of different examples of corrosion resistance in our parts. Oh, good question. How well does the Onyx matrix hold up to high temperatures in relations to HSHT fiberglass or other fibers? So Onyx has a heat deflection temperature of about the same as HSHT, which is good because as I mentioned, Onyx, is a matrix that has to be included in all of these parts. So it's about the same. It's about 145 Celsius, while HSHT is 150 Celsius. And so Onyx is suitable for those high temperature applications as well. Jesse asks, interested in fabrication of prosthetic sockets. I'm jumping around here. Collaboration production currently. We are working with a couple of different prosthetics manufacturers, and this is definitely a use case for our printers. So another question from Emmanuel. Usually TP composite materials needs to be consolidated. How can you ensure that the fiber is well impregnated or bonded with the matrix? So this is something that has gone through rigorous testing in our R&D team. And this is actually what makes our technology so proprietary, is that we're the only people who figured out how to bond these fibers with the matrix material. And so we have extremely high reliability with the printers, and those are making sure that the fiber is bonded. And our industrial series printers, like the X7, for example, actually has a laser mounted on the print head, which can do in-print inspection and make sure that those layers are laid exactly how you want them to be within the part. Question on what reinforcement is most commonly used by your customers. So this is a good question. It depends. Carbon fiber is obviously very popular because it's our strongest fiber. And I would say fiberglass is also up there, a really popular one, because it's the most cost-effective one. Whereas Kevlar and HSHT have more specific use cases with their material properties. A couple questions on resolution, maximum size part, stuff like that. Questions like this can be found on our spec sheets that you can find online.
So I see here there's a question on, do any of our materials have any medical applications? Yes, so long as the application is not in body. I don't believe our materials are body safe. In fact, I'm pretty sure they're not. But there are plenty of auxiliary applications within the medical field. I don't remember off the top of my head, but I know we use a lot of, our printers are used in many applications where we're 3D printing various fixturing for various medical processes.
And thanks for everyone's patience as I'm answering all these questions. We had a lot come in at the same time. Let's see. What type of support materials are used, and what is the method of removal? Breakaway, chemical, pressure wash, machine, etc. That's a good question. So our support material is Onyx is used as the support material as well. And these just break away. You can either take them off with your hands or with pliers, and they are pathed to be really easy to remove. And that way you don't have to have any other additional materials you're loading into your printer. Another great question on fiber laying. It says, it appears as though the reinforcing fibers are only around the periphery. Are they not distributed across the entire cross-section? For that part that was shown, it was an end effector. And so since that will be loaded and bending, concentric fibers are the most efficient way to add strength to that part. As I mentioned, if isotropic strength is what your application needs, that's also another way you can route fiber. Again, check out the Composites design guide to learn more about that. And there's a lot of really interesting information that answers more questions like that.
Looks like there's a few questions about specific material properties. I would direct you to our website at markforged.com. There's a materials page where we actually have data sheets with specific numbers for all of the things we've talked about today. So you can peruse that as well.
Question from Frederick on, is it possible to print in 3 dimensions, meaning fibers in 3D instead of 2D layer by layer? And the answer to that is no. The fibers are laid in layer by layer to make that 3D part. And as I mentioned, depending on how you lay that fiber, you can get that quasi-isotropic strength, even though you're printing layer by layer. Question from Michael. Can you take a part and rotate it in the software to change the grain structure, or does that need to be done in the design stage? This is also taken care of in our software. You can choose the orientation you print your part in, whether it's cosmetically to make it have the best surface finish, or if you want to make sure that it has the right amount of strength in the direction that you want. This orientation can be taken care of in our software. And actually, one of my favorite parts of our software is that you can actually click on a face of the part and it will automatically mate that with the print beds to really easily choose those print orientations. One question is, does Markforged make parts for customers too? So short answer is no. Long answer is, if you're interested in buying printers, you work with our sales team and our applications engineers to work through some sample parts to figure out if our methods are going to work for your use cases. And so through that process, you'll get benchmark parts printed and stuff like that to aid you in deciding to buy a printer. But the short answer is, we sell printers to empower our customers to make the parts.
A question here about biocompatibility info for our materials from Brian. This is related to the question I answered a little bit earlier. I don't believe we do, at least not in direct any sort of body or biological contact, and that's why I wouldn't say that our application is good for any sort of in-body parts that you'd be printing, but a lot of applications that we are good for are auxiliary sort of fixturing for various medical processes. I think we have a some sort of booklet on this that I can try to dig up, and I can try to send that to you, Brian, if that's helpful.
So one question: what causes the lower strength from traditional 3D printing, as you said? And this really just comes from materials. So traditionally, as I mentioned, 3D printing has been done in thermoplastics, which has kind of forced the industry into this bucket of doing, prototypes for fit and trinkets and stuff like that. And what we're trying to do is move away from that and towards actually useful parts that can be used on your factory floor, used in your products, with that higher, more reliable strength and better material properties. One question is Onyx available with different fibers? So I think what this question is getting at is Onyx is the matrix that's included in every single composite print. So whenever you're using one of these reinforcement fibers, you're reinforcing Onyx with that fiber. One question is the thickness different of the fibers. When printed, all the fibers print at 100 micron layer height, except for carbon fiber prints at a 125 micron layer height. Question on, do the two materials mix when printed as a composite, or are they two different prints? So how it works is, as I mentioned, the thermoplastic prints and layer by layer, and that fiber is also laid on top of that. So it's not a mixing as much as it is a printing from one nozzle and then from the other nozzle to lay in that geometry that you're looking for.
I'm going to keep going for probably 10, 15 more minutes. We're about 8 minutes behind on the questions. So if you asked your question 8 minutes ago, we're about getting it to it now. We do have a lot of questions, so forgive us for the delay.
Question: any more problems with sunlight than normal carbon fiber parts? No, Onyx is UV resistant. The only one of our materials that may have an issue with sunlight is Kevlar. But as I said, the Onyx matrix is going to cover the outside of the part in every case anyway, so that Kevlar will never be exposed to UV radiation. And so sunlight is not going to be able to degrade Onyx. One question: what is a typical fiber volume fraction? Assuming that's asking, what percentage of a typical part is fiber. Usually, it's actually pretty low, because If you've learned about beam bending theory before, Alex, one of our content engineers, actually went over about how to best route fiber in your part in one of our past webinars. But you actually don't need too much fiber to really give it that strength, especially with those concentric fills. If you put that high strength material along the edge of the part, you can usually get really high strength with, single digit percentages of the part being fiber. So a good question from William. You described the failure of carbon fiber reinforced parts as sudden and catastrophic, while Kevlar reinforced parts have a more gradual failure. Does that imply that a Kevlar reinforced part could have partial damage that is not very evident? So I would actually argue the opposite of this. So Kevlar, once it's starting to damage, it begins to deform. And you'll be able to see that deformity if you're really starting to get it towards that maximum load. And so that actually makes it easier to see once it starts to degrade, because it starts to, the fibers one by one start to fail, and it starts to deflect a little bit more. Whereas carbon fiber, it barely deflects at all. When carbon fiber breaks, it's actually at about 1% deflection before it snaps. So although it has a very, very high strength, it fails pretty immediately when it does fail.
See, we have a few questions about how long it takes to print parts. Time printing time is not our first priority. We want to make sure that the parts that you get are strong and that the surface finish comes out really, really well. So what we really compare print time to is more traditional machining processes, such as if you were to want to machine an equivalent part out of aluminum, and how long it would take you to actually request for a machine shop to produce that part for you and get it back. Obviously, 3D printing is going to be much, much faster than that. But if you want to know for specific parts how long it takes to print them, again, you can visit us at Markforged, and you can get a trial of our software where you can upload your parts and get estimates on print times.
Yeah, that's a good point from Marco. Although our print times are pretty comparable to other 3D printers, depending on how much fiber you have in it. The fibers do print a little bit slower than thermoplastic, but I rarely see any prints that are longer than a day, even if they take up the full build volume. If you compare that to machine shop backlogs, it's up to 10 times or more faster. A question on metal printing. Is the Metal X the only printer that prints metal? Yes, the Metal X is our metal printer. And then all of the composite printers only print composites. A question about the cost difference between the 4 different reinforcement materials. Also on our website, but fiberglass is about $70 per spool. Kevlar and HSHT are $99. And carbon fiber, if I remember correctly, is $150 per spool. Question, could the HSHT withstand large clamping forces from an injection molding machine? So it depends on how you want to use it with an injection molding machine. Would you be 3D printing straight up injection molds with HSHT? No, but a lot of our customers do make inserts for different molds to be able to get more complex geometries in their injection molded parts with HSHT, and it does withstand those clamping forces very well, which is why we designed HSHT to withstand those high temperatures, but also have that really high strength. A question on post-print operations that are required before use, like a wash or a post-cure. Our parts require no post-processing, our composite parts, unless you have to remove the supports, which you can just do by hand. It just takes a couple seconds. So they're ready. The parts are ready to go right off the print bed. Question about the size of the chopped carbon in the Onyx. Very, very small, almost powder-like.
A question about whether we can run other filament from other producers instead of Onyx. Our printers use our proprietary materials. That's just the only way we can guarantee that you're going to get reliable, consistent, high-quality prints every time. So Markforged printers rely on Markforged materials.
Yeah, our printers are actually designed specifically for our materials to give you that superior surface finish and accuracy of our parts. A question about working with metal inserts, like metal forming, presses, high impact with sheet metal. Great question. We actually have a customer is Centerline. Yeah, Centerline. Centerline Engineering Solutions. And what they do is they use our part. They have one of our printers and they print onyx reinforced with carbon fiber, and then they add steel inserts to it halfway through the print, and they use it to press. I think the sheet metal is 1/8 inch, so that would make it about that's about 10 or somewhere between 5 and 10. Yeah, about 5 millimeters, if I'm doing that math correctly. No, closer to 4 millimeters thick. And so, yes, sheet metal forming is definitely a good application of our parts. Question: what's the difference between reinforcement and continuous fiber? So continuous fiber is the material and that is used to reinforce. So you can call it reinforcement or continuous fiber. They mean they are one and the same. Question about outgassing properties in a vacuum. I'm not sure exactly what you're asking. Our parts for can be printed like watertight and airtight, but not depending on the pressure. And then in terms of any materials that are sloughed off of the parts, Onyx does release some caprolactin, which makes it currently not as usable for space applications, but that is something that we are working on. Let's see. Do you know of any customers that are using the continuous fiber of HSHT material for composite tooling for curing composite parts? I do not know of any off the top of my head. We may have them, but this certainly sounds like a really good use case. Depending on what temperatures you're working with, HSHT could be the right material, or maybe fiberglass or carbon fiber could work as well for that. I've heard your parts cannot produce solid fills for sufficiently large features. Can you elaborate on this? What are the limitations? Good question. It really, really depends on the geometry and size of the part. As with all 3D printing, very large parts with solid fill tend to warp a little bit. Our Onyx material with that chopped carbon fiber inside helps resist warping, and also printing with fibers helps resist warping. So on really large features, what we recommend if you're printing with reinforcement fibers is to reinforce it if you're doing it for that strength. We've found that it's surprisingly solid infills really do not add that much strength to a part. Which is why we really invented this CFF technology, so you could reinforce it with fibers. So instead of trying to do it with solid infill, you can get even higher strength with less infill, which actually helps you because your parts are more lightweight as well.
So I think we're going to go do about 2 more minutes of questions. We're so sorry if we don't get to your question today. I'm looking at 150 questions here, which thank you so much for being such an active audience. We really appreciate that. But we're going to run out of time probably. So I think Nick's going to answer just a few more questions that you guys have time to do. And then if we don't get to your question, you can visit us at markforged.com and you can actually request a consultation with one of our product specialists who can actually discuss your application in much more depth than we have time for today. And also some more questions about specific material properties, print bed sizes, printer specifications, things like that. Again, I'd encourage you to visit us at markforged.com and browse through the product and material pages where you can find in-depth data sheets with precise numbers for a lot of the things we've talked about today.
Question on what's the cost of 3D printing, meaning manufacturer costs, not raw material costs, compared with conventional compression molding or layup layers of composites? This is a really good question. So as anyone who knows about composite manufacture, it's a very expensive way to make stuff, mostly because the materials are typically very expensive, and then you have to pay for the labor of the layup. So you have to make tooling to make the shape of what you want to make, and then someone has to actually lay the fiber. Whereas with 3D printing, it's funny that you ask, you want manufacturing costs, not raw material. Well, the only cost of 3D printing is the raw material, because after you design your part, you don't have to do any CAM, you don't have to do any manual labor. All you do is send it to the printer, and then your part is made. So the cost of 3D printing is literally just the material costs, which is why a lot of our customers are seeing massive savings. Like with that Humanetics mold, like 99% cost savings, because they can just print it on their printer when they're not even in the office, and then they have it ready rather than paying for someone to machine it. Oh, good question. Carbon fiber's melting point is 1200 Celsius. How do you print with a temp like this in a 3D printer? If you all knew this, maybe you would be making the printers and not us. I'm just kidding. So our carbon fiber material is a proprietary material that we've designed to be able to be printed on our printer, so that we can deal with issues like this that you don't even have to worry about. A question, does Markforged print demo parts for evaluation prior to purchase? Yes, you can work with our sales and applications engineering team to figure out exactly how we can best serve your needs. Oh, good question about how dimensionally stable are Onyx parts. And William says, I have had experiences where plain nylon has absorbed moisture and swelled. This is a great question. Before printing, we keep our Onyx in a dry box, and that helps it, keeps it from absorbing that moisture before it's printed. Post printing, it does absorb a little bit of moisture, but we found that the dimensional reliability has been good even for precision applications. And again, this webinar is going to be available probably sometime tomorrow.
Yep. So we'll be sending out a link to the recording sometime tomorrow. And there is also a page on our website. If you go under, I believe it's Learn, there is a library of all of our previous webinars that you can check out there. So this webinar will also appear there as well. And I think, Nick, unless you have any other specific question you'd like to answer, I think we're going to slowly wrap things up for today. Again, if you have not tried out the software, our slicing software, I would encourage you to do so, specifically as it relates to this webinar. It's just a great way to actually see how continuous fibers and composite 3D printing can apply to your parts, because you can actually upload them into the software and play around with the fiber reinforcement, configure it as you wish, and actually have a 3D render essentially of what your part, or how your part's going to look internally. And along with that, you'll get estimates on print times and part costs as well, so that you're very well informed about exactly what this means for the parts that you're trying to produce. We've hit 150 questions here today. It's been a great audience. Thanks so much for attending and for your questions. And if we didn't get to your question today, I'm really sorry about that. Unfortunately, we are out of time. So I encourage you to visit us at markforged.com and actually get in touch there, and we can actually address your questions in more detail with some sort of evaluation or consultation, which is basically you can have a product specialist, again, totally free, no commitment required there. Just get in touch with you, and they can you can actually share what you're trying to work on, and then they can give you suggestions about how our process might help. But we're also a very straightforward company about these kinds of things. So if your application isn't great for our process, they'll tell you that as well. So it's just a really great way to just be more informed about how you can improve your manufacturing workflow with 3D printing. Again, thanks so much for joining us today. We hope you found today's webinar informative and helpful, and we look forward to seeing you at the next one.